So I'd like to start by thanking the organizers for giving me this opportunity. So today I will talk to you about spectral distortions and the challenges that we face to make these measurements. Most of this work has been done with in collaboration with Jens Kluba and Matthew Remaze and Andrea Raveni, who may be not here today, but I've learned a lot from discussions with them. Okay, so here is the plan for my talk. I'm first going to start off by telling you very briefly what are spectral distortions and what is it that we can hope to learn from them. Okay, the next thing is to say, okay, what are the planned spectrometer missions? What are the requirements to make these spectral distortion measurements? There are no missions that are as of now approved or on way to flying, but there are people have been trying to design missions to make these measurements possible. Okay. So to do these missions and then doing the forecast for them, I'm going to very quickly tell you what is the machinery that is currently being used to do the forecasts, what are the advantages and what are the drawbacks with this machinery. And I'll try to convince you that maybe this is a little simplistic, but it's something that you start with. Okay, and then finally, I will really talk about what are the ongoing efforts to building these real world foreground complexities into the forecasts. Okay, so we've measured the CMB spectrum extremely well. It's one of the best known black bodies that we have in the universe. And ever since we've actually measured not the CMB spectrum again, but we have been measuring the anisotropies in the sky to more and more precision over the past 2 or 3 decades. Okay, and the saga kind of continues. We are going to continue to do this with Lightbird and with the many more upcoming ground-based CMB experiments, with the primary aim of mapping out the polarized sky and getting to weak lensing, those being the two of the main goals. Okay, but other than the CMB anisotropies you see from the surface of last scattering, which happens at around the redshift of 1000, there's a lot of rich physics that happens before that epoch. Okay, because the sky becomes optically thick before that, we cannot really map what happens in the universe before that. But a lot of the physics that happens before a redshift of 1000 is actually encoded in the spectrum. Okay, and there are very definitive predictions within the lambda CDM cosmology as to what these distortions should be for the black body, for the CMB black body spectrum. Now, so that basically means that the so-called perfect CMB black body is not really that perfect. There are distortions that we expect, that the spectrum has distortions which makes it deviate from black body, but these are extremely tiny and we have not yet measured them. But if we did measure them, what we could do is we could probe phenomena that happens in the very early universe. Okay, so basically, if for at epochs above half a million, above a redshift of 500,000, you get a distortion which is called as a mu distortion, and below 10⁴, you get something called as a Y distortion, which is the same that you get from the distortion induced by the hot electron gas inside galaxy clusters. And then there is an intermediate regime, actually, where if you had some energy injecting processes like dark matter annihilation or things like that happening, they could actually introduce additional distortions to the CMB spectrum, but these are commonly not spoken of. Okay, so actually there's a rich plethora of spectral shapes which in principle we could go and measure. And of course there are the recombination lines, which is basically the familiar hydrogen transition lines, which happen in the early universe when the hydrogen and helium atoms are recombining, and these also leave a very characteristic spectral signature, which is again encoded in CMB spectrum. Okay, so the bottom line is that strictly speaking, the CMB is not a true black body. There are these deviations from it, and we can measure these deviations and learn a lot about the early universe. Okay, so like I said, there are these residual distortions, and actually these are examples. These are some examples of what the residual distortions could look like. But in principle, energy injection, these are the energy injection eigenmodes, what you see here in the top left. And these would give corresponding spectral distortions in the spectrum, which in principle we could go and measure. But from what we understand as of now, these are expected to be significantly small signals, unless there are some unexpected phenomena that are happening there, which is not captured by lambda CDM. Then you could actually have even these signals which could be larger. Okay. The other thing to bear in mind is when people usually talk about mu distortions, you're now these spectral distortions, these are typically probed by very, very small wavelengths, which are not probed when you just measure CMB anisotropies. Okay, so we would actually be testing the lambda CDM universe at wavelengths which have not been probed before. So we would be talking, we would be testing the properties of the universe at wavelengths corresponding to 1,000 to 10,000 megaparsec inverse. Okay, so this for those who are familiar and when you've heard this number that mu has to be 2 into 10 power minus 8, it makes an assumption of many orders of, it makes an extrapolation of the lambda CDM power spectrum across many orders of magnitude. Okay, and if there are any, if you do not detect it, then it clearly would mean that the power spectrum shape has to be different. Or if you see some excess power, then it could again indicate deviations from lambda CDM. So we cannot take this for granted. So spectral distortions actually provide this unique window of testing the lambda CDM universe in a new set of wavelengths. Okay, so not only that, not only can you probe early universe, you can also probe late time universe, because through via the Sunyaev-Zeldovich effect, these again, the late time, the largest collapse clusters in the universe have hot gas, which inverse Compton scatter the CMB photons, leaving these characteristic spectral signatures. And actually here is now a forecasted plot of what we could hope to achieve by making such a measurement. If you could measure the mean baryon pressure in the universe and what temperature it is at, you could actually be putting constraints on the average feedback models, basically constraining the thermodynamics of the low redshift universe. Okay. Okay. So hopefully I've convinced you through these slides. There are some example science cases which are particularly exciting, that just like with anisotropies, we've made huge strides in getting a deeper understanding of our universe. CMB spectral distortions offer another such opportunity, and these are separate measurements. These do not rely on spatial mapping, but on the mapping of the spectrum to unprecedented levels. Okay. Now, this has been done before, and it was done by Firas, and it not only measured the black body, but also put limits on what would be the amplitude of these mu and Y type distortions, and these are quoted over here. Okay. So there are definitive signals which provide unique insights, and which definitely motivate the measurements. And with the aim of being slightly provocative, this is unlike B modes where there is not a definitive signal, and you may not necessarily learn anything by chasing primordial B modes. Okay, but that's for a separate discussion. Okay. Now, what does the signal space look like? So I told you that, okay, there are all these spectra, but let's now distill down to what are the signals that we are primarily after. Okay, so what you see here, the red line is basically, we've measured, Firas has measured the CMB temperature to be 2.725 Kelvin. And this red line is just indicative of the corrections that we expect to hope to measure on the CMB temperature. Okay, so this is nothing but the derivative of the black body, but these are corrections that we will need to measure, because to measure something like mu, which is shown in the orange curve here, you would need to be measuring the CMB temperature to nanokelvin precision. Okay. So basically, you have the green line and the yellow line, which represent the Y, the mean Y distortion signal, and there is a relativistic correction to this signal, which is shown in the yellow, which would allow us to measure the temperature of the electron gas, the mean temperature of the baryons in the universe. Then you have the mu distortion, which is in orange, and then the purple line actually shows the cosmic recombination radiation spectrum. Okay, so these are basically the green, yellow, orange, and purple are basically the signals that we see to measure. Okay, so what are the requirements to make such a measurement? So as you would have, as you might have, if you saw the scale on the previous slide, you would have, the sensitivity requirements are of order of 0.1 Jansky per steradian. Okay, Why so small? Because the signals are so small. You now need very many channels and with good frequency coverage. And the main reason is that, as we will get to them, there are foregrounds, and there might be foregrounds which we have not yet seen when we measure to these precisions, and we need to have enough frequency channels to kind of mitigate their effects. Okay, you need good channel calibration. So unlike WMAP and Planck, which were essentially differential experiments, they were not sensitive to the monopole in the sky. Okay, so here, all these signals that I'm talking about, I should emphasize, are actually monopole signals. Okay, so we want to measure the sky average. So we cannot throw out the mean signal that we get from each pixel, because that is where the signal lies. Okay, now we need the sky coverage and resolution are, we need, because it's a monopole signal, one could argue that one needs good sky coverage. But this is again an instrument optimization question as to whether you could focus on smaller fractions of the sky, something like what BICEP is doing for B modes, and drill much deeper and get much more sensitivity. Okay, similar questions are there for resolution. So even though you're really wanting to measure the monopole sky, the question is, do you gain from having higher resolution, because it would then tell you more about spatially varying foregrounds and allow you to distinguish foregrounds from signal. So these are all questions and things that can be optimized when making these measurements, but there is no good answer as of now. Okay, most experiments that I told you about aim for a full sky coverage and with a resolution of around 1.5 degree. Okay, 1.5 degrees beam. Okay, so yeah, like I said, most of these FTS concepts, these are the kind of sensitivities, the experiments which have been planned, proposed, and not been particularly successful are what I show here. But all of them are targeting with these frequency coverages at these characteristic sensitivities and a 1.5 degree beam. The only positive thing here is, of course, the Voyage 2050 initiative. Now, this was the spectral distortion measurements were actually recognized by ESA as one of the future science targets, and as one that could be targeted in 30 years from now by ESA itself. Okay, so that's one good news in terms of experiment planning. Okay, going on. Okay, what does the foreground sky look like? Just one second. This thing is okay. Yeah, the foreground sky looks something like that, where you have all the main foregrounds that we are aware of from the measurements that we have. Of course, this does not have now the ZODI and maybe a few other things that you can think of, but these are dominantly the foregrounds that dominate our sky. Okay, so you have synchrotron, free thermal dust, CIB, you have AME, CO, and the sum of them is what composes the total foregrounds. Now, the reason I say this is it's 11 parameter model, that is assuming that CIB, thermal dust are given by some modified black body, which needs 3 parameters to characterize each. Synchrotron is a power law with 2 parameters, and free we assume is just given by 1 overall amplitude. Okay, we will get back to how accurate these modeling is in a few slides. Okay, so moving on. So now here, composing now our signals and our foregrounds, this is now what we have as a model of our sky. Okay, this is actually a very basic model, but it already is fairly complicated. And to model this, you would need to fit for 16 parameters. Okay, if you wanted to solve for all these components. Now, let's stick with this for a few slides. So basically, the current forecasting procedures assume all the assumptions that I told you in the previous slide. They assume these simple SED forms for these different foregrounds. Okay, they linearize them, and then they basically set up a Fisher, and which allows us then to make an SNR forecast on how well you can measure the cosmological signals in presence of these foregrounds, which are characterized by this 11 parameter model. Okay, and when you do this, you can easily get forecasts like these, which basically tells you how well you would be able to measure the mean Y or the relativistic correction to the mean Y. That's basically characterized by the electron gas temperature or the mu distortion amplitude. The A dissipation now is the total distortion. So I will not be able to clarify that right now, but I can come back to that towards the end of the talk if somebody is interested. And of course, what you see here are the errors with which you'll be able to measure the CMB monopole temperature. Anywhere that you make a detection of mu, you can see that the error on the temperature is of order of a few nanokelvin. Okay. Another interesting thing I want you to note is that one of the exercises that I did was to pass through this Fisher framework, just the Firas sensitivity curves. Now, again, there are some assumptions with what foregrounds go in when you do the Firas analysis. I will not be able to detail that right now, but ask me. But it's interesting that the Fisher forecast yields error. These are now error bars, so you'll have to multiply them by 2 to get 95% upper bounds. These are quite compatible with the numbers that are given by Y and mu. So one may think of this as a reasonable setup, which at least works for Firas. But for reasons that I told you before, or just because it works reasonably for Firas is not reason enough to believe that it's fair enough to do it for higher sensitivity experiments. Okay, and the main reason is that you cannot be assuming that foregrounds are characterized by the simple SED form on the monopole spectrum. Okay. So given this Fisher setup, not only can we now do assessment of how well we are able to measure these spectral distortion signals, we can actually become a little more ambitious, which is what we did, and ask, oh, if you measured the cosmological recombination lines extremely well, what kind of cosmological constraints now can you get from these CRR measurements, okay? And this is just an example slide just to show you that in some dream world, if you were to measure these in a few decades from now, hopefully, measure the cosmological recombination radiation at very high significance, you can actually be doing cosmology with it and constraining cosmological parameters, okay? But this is the strength of Fisher that already with this simple setup, it allows us to answer some of these questions, okay? So, but like I already argued before, given the orders of magnitude jump that one is doing in sensitivity, one cannot assume the simple SED models to accurately describe models. Okay, so then what does one do? What one does, let me walk you through the argument for the moment modeling of foregrounds now. So this, I'm going to take a modified black body as an example, but in general, this could be generalized to any other SED form. Okay, so let's say you have just one cloud along a line of sight and it emits with some characteristic temperature and some spectral slope alpha. Okay, this is what we typically, one of the assumptions that is there in the Fisher forecast, and also when, say, the GNL provided these fits for beta and temperature. Now, one of the first things to notice is that, first of all, one cloud assumption along a line of sight may not be reasonable. Second of all, the SEDs that I was referring to before were the monopole SEDs. Okay, that is the sky averaged SED. And as you can see over here, the spectral index and temperature actually vary across the sky. So now when you add up different modified black bodies, which have at different temperatures, either because you have different clouds along the line of sight or because you have different emission properties along different directions, the sum is no longer characterized by a modified black body. Okay. So this integrated SED is no longer a modified black body, and it cannot be accurately described by such a modeling. Okay, so what then can one do is one can say one can argue that, let's say there are some parameter distributions there's some distribution of clouds which emit with some characteristic spectral parameters, and there's some distribution that characterizes that. And each cloud itself is emitting as a modified black body. Then one can actually do a moment expansion, which is basically say you expand the SED around some pivot parameters. And then what you're left with is this thing in this blue square that you see here, which is nothing but the moments of these spectral parameters. As you can see, these are weighted averages of the spectral parameters around the pivot around which the SED is estimated, okay? And the quantity in the blue is now some parameter which you can fit, that you do not know the probability a priori, but what you do know is now when you take the derivative of the spectrum with respect to the parameters, they give rise to new spectral shapes. And this, I'm going to argue, is going to give a good fit to a system like this, where you have multiple clouds intensity from multiple clouds with different properties and combining. Okay, so when you do this, you can actually write the effective, you can think of it like a deconvolution problem where you do not know what the ACD or the best pivot parameters around which you want to expand, and you can solve for the map. So it's kind of like a deconvolution problem where you don't really know the kernel. It's not that important to know the kernel because for any given kernel you can solve it. But if you want to do it, you want to reach a desired accuracy with a minimal basis set, then you want to optimize over what your kernel is. Okay, but these are very specific details that we don't need to go into. But the basic idea is that you take these moments and you form these basis set of ACDs. These are not necessarily orthogonal in the frequencies that they span. You can, let's say, for example, Gram-Schmidt orthogonalize them. And here's an example of a Gram-Schmidt. These are some of the basis functions which are shown here on the plot on the left, and they are properly orthonormalized. And here is an example now of a sum of two modified black bodies. And in principle, if you did a modeling of this sort, you could model to arbitrary precision, only limited by, in this case, the numerical noise in your computer, or in practice, you would be limited by whatever are your measurement noise. Okay, so the main idea here is that this moment description or this effective modeling of foregrounds can actually describe these superposition of ACDs rather well. Okay, so that was just an example of two black bodies. Well, now here I'm showing you an example of what you do. What is done here is you take ISM and you find out what is the average sky ACD by masking 30% of the sky and averaging the ACD over the rest remaining 65% or so. And in the figure on the left, actually what is done is we've included both the synchrotron and free tree, and on the right is actually the dust component. Okay, and here effective, now this is for those of, again, the Python sky model uses what we have measured about the foreground sky from Planck as input, and it simulates this sky on that basis. And what I'm showing you here is that the moment modeling actually works rather well in modeling these moments. Okay, but bear in mind that Python sky model only has for each pixel on the Planck sky is characterized by one modified black body. Now then that may not be accurate when you go to higher sensitivity, and one may expect a similar order of magnitude of moments arising just from the line of sight averaging in each pixel in Planck. Okay, maybe with Planck we're just not sensitive enough to see right now. Okay, so now I've told you that if you there's some effective modeling of foregrounds that one can do. Okay, but the question is, do we need to accurately model the spectra, or could we circumvent this by exploiting spatial information to clean foregrounds? Because we know that foregrounds are spatially varying, but our signal is actually constant. So just like for the CMB anisotropy measurements, the way the variance minimization helps in mitigating foregrounds, the question is, can you do the same thing here and actually not have to model all the spectral degrees of freedom of the data and get away by some kind of variance minimization technique? Now, so a very quick recap of the ILC. If you have the data which is characterized by C being the components which have all different spectral ACDs and tau being the maps, then you can actually write a simple ILC solution. If you just want to solve, let's say for the CMB, you would put in the CMB spectrum there, and this gives you a solution to the map. Now you can generalize this to saying, okay, I want to solve simultaneously for the CMB and TSZ while nulling the contamination between these two D components. And you can actually show that you can construct a filter like this, which achieves exactly that. Now, on the basis of this, you can actually generalize this to a moment ILC, where instead of just taking CMB and SZ or just the signal vectors as your ACD vectors that span this space V, you can actually add also foreground moments in there. And now you have a general moment ILC, which gives you simultaneously solutions for all the components of which you inject ACDs of into the V matrix. Okay. Now, as one increases the span of V, the solutions approach those that you expect from pure parametric fits. Okay, this is something that you can show formally. So basically, if V spans all degrees of freedom, you can actually show that the filter for this moment ILC or the constrained ILC actually reduces to this. And in this case, you can actually show that it reduces the covariance of the maps reduces nothing but to this equation that you see here, which is nothing but the Fisher error estimate that we have been using to do the Fisher error estimates. But again, the limitation is in what we say is spanning V, okay? What spectral degrees of freedom completely describe the foregrounds of the microwave sky. Okay, so this is a very nice framework in which actually you know the ILC method and you can actually connect it to the parametric methods, and we also understand what the relation is to the Fisher that we are employing to do these forecasts. Okay, so to build in realism, one of the things that now we've done is to show in this work that ILC-like methods can be used to actually extract monopole signals. So we started with generating simulations at 4 different sensitivities, a channel coverage of 30 to 3000 gigahertz with the 30 arc-minute beam, and assumed only over here, we just assumed the dust model, and we do this ILC on small tiles, okay? And we assume a mu distortion amplitude, which is 100 times smaller than Firas, okay? So it's not quite at 2 into 10 power minus 8, it's at around 10 power minus 6, so around 100 times larger than what lambda CDM is. But this was just to demonstrate and that an ILC-like method who can help you recover monopole signals, okay? And this is just an example of the solutions that we get at one of the, for simulations at one of the sensitivities. So let me take a few minutes to explain this slide. So what we have done, if you look at the top plot, which goes from left to right, you start by solving for CMB alone, then you solve for CMB and Y, then you solve for CMB, Y, and mu, which shows this. And then you progressively add the foreground moment vectors, progressively, solving for the different orders of the moments. And then you see that on incorporating the second order moments for dust, you actually start again, because you're solving all of these simultaneously, only after solving for second order moments do you start seeing that you're actually recovering the CMB, the TSZ sky, which was input. So by the way, the rightmost plots here show what the injected skies look like. And the ones on the left over here show what the recoveries are, okay? Now the mu map, as I told you, is a monopole, so it's just constant across this field. You can't quite infer from this whether we are recovering the monopoles or not, but we will come to that in a minute, okay? What we see over here are actually the foreground moment maps. And as you go progressively from 0 to 3, so there should be around 9 maps that you progressively recover, which starts from the amplitude, the spectral index, the amplitude and the spectral index derivative, the amplitude, spectral index derivative, and the temperature derivative, and so on and so forth. You can get more and more, you can solve for the moment maps, simultaneously solving for all these maps, okay? So, okay, this is very nice. This is just the maps, but what we really care about is the monopole measurement. And what I show you here is actually, okay. So the plot on the left is the CMB, the Compton Y, and the mu distortion amplitude. And the middle panel is showing you what is the bias in terms of standard deviation. Okay, and the bottommost plot is telling you what is the error estimate on the monopole. So basically what I want you to pay attention to is this thing over here, which is showing you that the mu measurements are, first of all, the bias that you see depends on the sensitivity of the measurements, in this case, the simulated data sets. And then with different sensitivities, as and when you increase the moments, you actually see the bias diminish and become very close to 0, okay? And you get an unbiased measurement of the mu signal with this ILC-like method, okay? The same is true for Y, because you are also interested in measuring the mean Y. And the CMB temperature here is nothing but the correction that you expect to measure to the CMB temperature, okay? Again, the units here are in units of the sigma, the standard deviation units here are in units of the input signal, okay? So the main message here is that with the help of moments and an ILC-like method, the semi-blind moment ILC method that we've devised here, we are able to show that you're actually able to make these monopole measurements, though we are right now working in a restricted setting where you accounted only for one of the foregrounds. Okay, so with that, I will stop. Here is the summary for my talk. So I think SDE science is exciting with many specific science targets that probe the universe at different epochs of its evolution. Not only that, I think it probes the universe on a unique set of wavelengths, and testing lambda CDM on these scales should be an objective scientific requirement. Okay, foregrounds pose a very real challenge to making these measurements a reality, but a marriage of moments and ILC methods can lead to a powerful tool to mitigating these challenges. But this is only a part of the story, right? Because this is only a part of the work. There's lots more to be done, because what I've told you here, it's kind of simple to say, oh, how do you do foreground modeling for ACDs, which you can characterize well, like, for example, synchrotron and dust and CIB. But let's say we want to also worry about CO and AME, then you have to ask, do we have moment models for those other foreground components? We have to ask, how could we exploit other experiments like the upcoming CMB experiments, which would be measuring the CMB sky at competent sensitivities at very high angular resolution, how we can use those to mitigate foregrounds, the galaxy surveys, the line intensity mapping, and instrument optimization. And there are many more such questions that we need to answer to make this a reality. Okay, with that, I will stop and take questions.